Testing, testing. 1, 2, 3. I think we're live. Yes, we are live. Okay. Welcome everyone to what I believe is the second installment of our weekly roundup. Let me explain a little bit to you all what the weekly roundup is. So if you've been following me for some time now, you know that typically on the weekdays, let's say from Sunday until the following Saturday, or really I guess until the following Friday, I'm creating LeetCode live videos where I go through questions in LeetCode and I just stream myself doing them. Now I do these questions in a very particular order. I have been going through every single easy question. Really my goal is to go through every single question on LeetCode and just stream myself doing everything, in the hopes that people watching this will hopefully learn a little bit. They'll see someone, struggle through questions. They'll hear me think about different trade-offs and talk my way through what is hopefully an optimized solution. Been doing this for almost 2 weeks now, and I'm very happy with the results. I really want to thank the community for being so supportive. I know we've had a couple of recurring subscribers coming back, so that makes me very happy. We're nearing the 100 subscriber mark, which I think is phenomenal. So very happy about my growth. I'm very happy about the community. I love the participation that I've been getting. So I really hope that for more people out there, they're joining in on these videos and hopefully benefiting from it. Tell your friends if they're also looking to practice some LeetCode, to join in on the fun. Always looking to hear from many different people's perspectives and sort of, learn also myself. So this week was really good because we passed the 100 question mark. So now we're past 100 questions on our journey to do, all 585 questions on easy questions on LeetCode. We're making some decent progress. So I think if we keep it up on this trajectory, we'll be making, we'll be hitting the 585 in no time. And then we can move to the medium. To be completely honest, I'm very excited to make it to the medium because that's really where I think the true bulk of value will come from. But it's going to be an amazing journey going through all the easies. So I think that's also worth mentioning. Something else that I want to talk about is a list that I've created. There are plenty of lists out there, LeetCode 75, Blind 75, NeetCode 150, all phenomenal lists. And I think you should absolutely be looking at all of these lists all of the time. This is what you should be doing to be able to make yourself a well-rounded problem solver. I decided to add my list into the mix by creating my own list. And these are a list of questions that I think are great questions to go through. Right now, this is just it's a dynamic list, but it's hosted on LeetCode and it's just being managed in this way. What I would really, really like to do is possibly create some site or something that I can point people to where all of these questions will essentially just be linked to the YouTube video where I talk about them. I think that would be really cool. That'd be really fun. Something that I might do soon, so keep a lookout on that. This is why I'm really excited to one day soon get the community feature. That way I can tell you all about these things and get the community more involved. I think it'd be really neat. So without further ado, let's get into the weekly roundup. Typically what I do with weekly roundup is I just start going back to all the questions. I see the ones that I haven't solved to sort of fill in any gaps and then sort of go from there. So let us go through this. And I want to look at questions that we haven't solved, right? Obviously, we can't do anything with premium right now. I may do that. What I might do is if at some point, I'll make it a goal of mine that maybe if I hit the 1,000 subscriber mark, or when we're done with all the easies, I might bring in premium questions into the mix. So I think that'd be pretty neat. So we're just going to go through ones that we either attempted and didn't finish or just never got a chance to do. So I think this is the first one here. So this stream may run a little bit longer than an hour. I think that's sort of the intent here because we're just going to try and solve as many of these as we can. It will at least be an hour, and then we'll sort of go from there, trying to decide how we want to approach this. Okay, so without further ado, let's just get right into it. So count equal and divisible pairs in an array. So we're given a 0-indexed integer array nums of length n and an integer k. Return the number of pairs ij where 0 is less than or equal to I, which is less than j, which is less than n, such that nums of I equals nums of j and a times j is divisible by k. So let's think about this, because I haven't, let me see the example. So nums of 0 equals nums of 6, okay, and 0 times 6 is equal to 0, which is divisible by 2. And we're looking for the index. Okay, nice. Now, what happens if I were to sort all this? What would this look like, right? I'm not sure if this is something we considered last time, but I think that's always a valid approach. Something that I've learned is not to, sometimes I get scared to try things out because I immediately want to try and optimize, but perhaps maybe the best, I think it's called the BCR, best conceivable runtime. Maybe that is nlogn, where nlogn in this case would be the quicksort function. Maybe there isn't something better that we can do. So I would always encourage you to talk to your interviewer, let them know exactly what it is you're thinking, because perhaps that's the best you can already do. So don't spend time trying to optimize. I think there's also another saying like perfect is the, or premature optimization is the root of all evil. Just, you know, shoot your shot and go for it. That's what we're going to do here. We're going to try to sort this and see if that sort of gives me hints as to how we can approach this. So we have 2 1s, so we have 3 2s, and then 2 3s. Now, I think the reason I can't do this is because, let me see, nums of I equals and 0 and 6 equals 0. If it was the other way though, like 0 and 6, like this case would be 5 and 6. 5 times 6 is 30, and 30 divided by 2. 30 is divided by 2, right? 6 times 5, that's 30, right? Yeah, maybe, I mean, this could be a way of going about this. Let me see something. Number of pairs where 0 is less than I, and I times j is divisible by k. That could be a way to start it off. So let me just like try that out, right? Like what if let me see if I sort it, do I get the same thing? So here I have my I, and I start sort of looking through this, and I say, you know, I found a pair because this one is equal to the previous one. These are both equal, so that satisfies this first condition. 0 times 1 is 0, which is divisible by 2, so that's fine. We get to this next piece. This is 1 and 2. 1 times 2 is 2, which is divisible by 2. So that's 2 pairs. These are the same. 0, 1, 2, 3, 4. So 4 and 3 is 12, which is divisible by 2. So I think here we still get 4. So let's go ahead and try this out and see what we land on. So I'm going to start off by sorting my nums. So I'll say const sorted nums is equal to nums.sort a, b, a minus b. And then from here, I can start sort of, right? I can say I want to now get the pairs for let I equals 0, I less than sorted nums dot length I plus plus. And I guess really we can start at 1 because we're never going to have a pair at 0, right? And if we just have an array that's of size 1, which I'm not even sure, nums.length, it could be equal to 1, we'll just return 0 for that, right? We'll never do anything. So let's actually start here. So we have 2 different cases. So if nums of I is equal to nums of I minus 1, and let's do I times I minus 1 modulo k is equal to 0, right? Because k is 2. And in terms of order of operations, I think this would work, right? If nums of I equals nums of I minus 1, and I times I minus 1 modulo k equals 0, then we can just say pairs plus plus. And we can return pairs here. So let's think about this. Let's see if this works. Let's run it at least for that first case that we had. This gives me a 1. So I think here, yeah, so the mistake I made here is I'm still referring to nums when I really should be referring to sorted nums. And what I'll do to make this a little more readable is I'll sort of split this up right into 2 separate lines. That's a common thing that I see. Let's run this. So we have 2 and 4. Not exactly what I was hoping for. I have a feeling that it might be because of some weird thing with order of operations here, perhaps. 0 times 6 equals 0, which is divisible by 2. 0 times 6 is 0. So 0 times 6, 0 modulo k equals 0. 2 times 3 is 6. All right, so 2 goes into 6. That's fine. 8 divisible by 2, 12, which is divisible by 2. So what is it that we're missing here? If we're at the 1, again, if we sort this, so let's get our array here. Let's do the sorting. 1, 1, 2, 2, 2, 3, 3. If we have that I that starts at 1, if sorted nums at I, which is 1, is equal to nums of I minus 1, so they're both 1, and I 1 times, oh, I see. So this, yeah, we're going to need another parentheses in here, right? I times I minus 1 modulo k equals 0. Let's run this again. 4 and 4. Okay, let's go and do the next one here. See how this comes along. 4 and 0. All right. Let me just, I'm changing something on my phone real quick. Okay, let me go ahead and submit this. Let's see what we get. Okay, so wrong answer here. And let's try and figure out why that's the case. So we got a 3 when we were expecting 18. So that's like wildly off. I feel like there's probably something maybe simple I'm missing here, but let us dive into it. That's exactly the point of this stream, right? The first thing we need to do is we want to sort this. Now, honestly, I'm just going to sort this in the DevTools, and we can do this. We can do const sorted equals this, sort A, B, A minus B. I think I maybe left, no, that's fine. And here we should be able to do copy sorted. So the copy method just copies this and puts it on your clipboard. So hopefully now, okay, well, I did get it sorted, but it didn't come out in the way that I was expecting. I'm going to open Visual Studio Code real quick. You won't be able to see this on your screen, but the reason I'm opening it is because I have prettier. And ideally, this should format it nicely for me. Is it not? Well, if anything, I can do like multi-line formatting. Just bear with me while I get this all sorted out. All right. Looks better. Let me undo this and put it under here. Okay. So we got I'm not sure. Oh, the 7 is the number it needs to be divisible by. Okay, cool. So it might be because I'm losing the positioning here. The question here might depend on the position, and that position gets altered when we sort. So let's think about if this will still work. So I have an I here. I just want to look for any time they're the same, right? All these are the same, but 1, let's see, like 1 times 0 is 0, 0 by 7. Okay, that's divisible. And we have here 1 times 2 is, yeah, so because we're essentially doing this number modulo 7, right? So 1 times 2 is 2 modulo 7. That's not going to work. Then we get 6 modulo 7. That doesn't work. 12 modulo 7 doesn't work. Let's see. We get, this is going to be 5 times 4. 20 modulo 7 doesn't work. And then now we have, these don't even equal each other. So we go all the way over here. And now we're at what? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 8, that's, let me see, 9 times 9 is 81. If I subtract 10, so that's what, 72? 72 modulo 7, I don't think that works. So yeah, I think here it has to do with the positioning. I'm losing information by sorting it. So we almost got there by sorting it, thought that would work. But yeah, it looks like we're going to need to figure this out in another way. So could I use, there's a very sort of famous pattern called a sliding window. I don't know if it would necessarily be sliding window, but maybe, yeah, how would I know when to increase or decrease? It's like I'm always looking for pairs. That's got to be the first thing I do. There are 4 pairs that meet all the requirements. What if maybe, because like, what am I losing? I don't really care about the pairs, right? I just want to find, I was almost thinking about making like another data structure to keep track of indices for me, but I feel like that's also going to get cumbersome because a 2 can be mapped to multiple, and now I'm going to have to be responsible for sort of like going through that indices array and knowing where I'm at, and that seems like a little too much management for a question like this that apparently is easy. So there maybe is another way that we can think about this. Number of pairs, 0 is less than I is less than j is less than n. I times j is divisible by k. 3, 1, 2, 2, 2, 1, 3. If I'm going through this, if the first pair I find, what if we use a 2-pointer technique? Will that work? But how do we know? And like, why wouldn't I skip over others? Well, let's see. If we had 2-pointer here, I can see that, okay, these are the same and the i's are fine. But now when I get to my next one, how would I know when to stop going? Like this could be one, and then maybe this is one, and that's another one, but then, yeah, I'm not sure 2-pointers can work here. We definitely need to find pairs, but we also need to find I times j is divisible by k. Is there a way to find all the places where I times j is divisible by k? Like, how many places is I times j divisible by k? And then if we get all those numbers, we just count where they're the same. Let's think about this. I times j is divisible by k. So we can never have a number. Does that mean it always has to be a multiple? Right? Because anything that's not a multiple of 7 can't be divisible by 7, right? So if it's like 14, that would work. 21 would work. 28, 35, etc., etc. Right? Because any of these, like this is a 2, 2, 2, oh wait, 8, 6, these are all multiples of 2. So do we just maybe need to find everywhere where we get multiples of like the k? So like 7, 14, 21, 28. Is this a way that we can sort of go about doing it? I times j. How many times can we do? I guess if we just did that, and we just did, so what if we did, oh, and 0, right? Like we'd have 0. Now what if here, now I'm kind of amending my solution here. What if I had like an I and a j? This is 0. And like I'll increase this until I get to another multiple. So I can say like, so 1, 2, 3, 4, 5, 6, 7. Okay, that's cool. And then I can be like, okay, so I found 0, that's 1, let's say. I found another one where it's just like 7 times 0, that's fine. What if we had 7 times 1, that's okay. 7 times 2, that's okay. 7 times 3, that's okay. 7 times 4, 7 times 5, 7 times 6, 7 times 7, okay. Now do I continue? How many do I go for the next time now? 18. I times j is divisible by k. We can always, I can sort of like store these in a map perhaps. 7 times 7, okay. Now maybe if these are the same, I start going like 8 times 7 is 56. Is 56? No. So when do we stop? That's the question. When do we stop? If we're bounded, like let's say this one, let's take a smaller example. because maybe this will help me. If we have an I, like how many can we do here? We have like 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. I mean, we could do a loop like this and just get every pair. Doesn't seem, yeah, I guess we can do that. We can get every pair and just see. Let's try this out. That will be a quadratic time solution. I'm certain that is the brute force solution, but we'll at least get something that we can mess around with. So far we've tried using sorting to be able to get us to the answer, but let's see if we can try doing this quadratic solution that will have a nested for loop. So we're going to generate all the pairs. So we can say for let I equals 0, I less than nums.length, I less than nums.length, I plus plus, for let j equals 0, because I think here, yeah, we're saying if 0 times 0, yeah, j is less than 0, j is less than nums.length, j plus plus. Or I guess we can make this 1 because we're already considering the 0, but 0 and 0 are also the same, and 0 times 0 equals 0. Okay, so here we can say if, same condition, right? If nums of I is equal to nums at j, and here we can say I times I minus 1 modulo k is equal to 0, we say pairs plus plus. So let's do let pairs equals 0, and then return pairs. Certain that, like, even if we get the right answer here, I really feel like that's not the right way to go about it, and we didn't even get it here, right? So let's see, will this always guarantee, oh, this should always be, we should always start at I plus 1, because I needs to be less than j. Okay, so we're off by 1 here. We're counting 1 more than we have to. I less than 0, or I equals 0, I less than nums.length. Okay, j equals I plus 1. Oh, wait a second. This should be I times j is divisible by k. Why did I do I minus 1 here? Like, I just thought about that. Why did I do I minus 1? That's weird. I have no idea. Where did I get that from? Okay, that's 4 and 0. Okay, so this works. We're generating every single pair, but wait a second. That's a crucial mistake, right? That can wildly change our answer. So I mean, let's go back to what we had before. Okay, wait, I still want this to be big. Let's just delete all this. Let's not do this piece. Let me take the one that I failed on. Let me open this just so I can copy the input here. And we can use it as part of our test cases. Let's see this. I times j modulo k. Oh, okay. That's why. Let's think about this though. Maybe this part is I times j. What would be? Yeah, wait a second. Number of pairs ij where 0 is less than or equal to I. Yeah, this shouldn't equal. I needs to be less than j, right? So perhaps here, maybe we should do I plus 1. And then we should say that ij, where j is the next one. Could this change it? Although this feels like it's really just the same. This is just sort of the same thing the other way around. I and I plus 1. I times I plus 1. Let's get that piece right. Let's do this. 4, 0, 3, and 18. Okay. are we just always comparing 0 is less than or equal to I? Okay, I is less than j, which it will be. Numbers of I is equal to certain numbers of I plus 1. 9 times j is divisible by k. Let's see. What's the best conceivable runtime here? N square root of n. Okay, so it's not n by n. It's just n square root of n. Why do we only have to go halfway? N square root of n. So instead of n log n, maybe for each one we just take equal and divisible pairs in an array. Traverse indices with same values. Hashing solution. Easy brute force n squared approach. Hash map and brute force easy solutions. Let's see what this one is here. Can we do better than brute force? We will need to solve a follow-up problem. Check this post for intuition. Count array pairs divisible by k. For each number, collect the indices in the increasing order. Track count of the GCD. Wait a second, I want to see one that's maybe a little bit, but of course this doesn't explain itself well. Brute force one line. All possible pairs and checking if they're good. Hashing solution. This is interesting. So why does that work? Let's see. For a number, go through its indices, track count of each greatest common denominator. For each index, check its greatest common denominator, ik, against GCDs for previous indices. I'm glad I checked your solution before contest 281. K is at most n, so the number of factors should be the square root of n. You can check the constraints. Most 2 square root factors. Can you explain how it's O squared root? I like this one. Here's the Python version. GCD map can be hoisted out of the loop and reused on each iteration. The following remix does that and a few other things. I'm not certain of the utility of doing this, but it might be worth benchmarking in real world use. I would really, really love to go through this and try and understand it. For each number, collect the indices in the increasing order. Okay, that makes sense. All right. For a number, go through its indices. Track count of each greatest common denominator. Does he have? Is GCD just I'm guessing that's just auto and GCD count GCDs. Res plus or equals GCDI times GCDI modulo k equals 0 or count. This seems very complicated. But the thing is, so many people are talking about how good it is to understand. Read more. Oh, is that it? There's no other. Wait, there's a lot of discussion here. Most votes. Can you explain? Took so much time to understand. Okay, I guess they're not showing any more here. Well, we solved it using the quadratic solution, which I suppose it's all right. I've said a lot in these streams where I'm thinking about the practicality. Actually, I'm not going to make any excuses. You can learn it if you want to. Certainly very clever to learn it. You probably will learn a lot from reading through it. But I'm at least happy that we solved this when we weren't able to before. I think that's a win in my book. And according to what I see in the... I was really hoping... Oh, and I guess I can't even... Can I go to the submission that was accepted? Memory usage. So we're just keeping track of all pairs. Let's see. Let's see what the time complexity is here. I mean, we're getting consistently 74%. I'm pretty happy about that, especially for it being, look at this, 91.91. Of course, we can always do better. Even the best people can do better. But again, for practicality's sake and for this stream, I like this. And again, we couldn't solve it before, and now we can. So I'm gonna like this question. Did I already add it to my list? I have not. Let's do that. And let's go to the next one here. So minimum time visiting all points. I think this one was really cool. Yeah, this one is tough. On a 2D plane, there are endpoints with integer coordinates. Points I equals xi, yi. Let me step out for a moment. I'm going to get some water, and I will return shortly. Just give me 1 second. All right, we're back. Let me just make sure we got audio coming through. Okay, sweet. Yeah, hopefully no one joined like during that time and they were like, man, what type of a stream is this? It's just quiet. Okay, cool. Minimum time visiting all points. So this one we definitely need to draw, right? Endpoints with integer coordinates return the minimum time in seconds to visit all the points in the order given by points. So I think one of my initial thoughts was like, could we just use the distance formula through all the points? But it doesn't give us the optimal path. This must be like, like, is this necessarily a graph problem? When I think of optimal path or shortest path, typically I think of BFS, like breadth first search. So it's just like, is that what I'm expected to be doing here? I'm not entirely sure. Let me see. I'm getting some bitrate is stream bitrate of 128. Just looking at something here. I'm being told the audio stream's current bitrate. All right, let me see. Audio stream bitrate of 128. I'm not sure I can change these settings midway. Just looking at something real quick. So for audio, output audio bitrate 320. Interesting. I'm hoping that's because of a weird like quality issue. Okay, I see. I'm not getting that notice anymore, so that's good. Okay. So one optimal path is 1 1 2 2 3 3, and then 3 4 2 3. Like, how do we know? Okay, I think I just thought of something, but it's like, seems pretty intense, actually. Okay, hopefully the audio is okay. I'm getting notice that perhaps the bitrate is lower than the recommended bitrate. Did I do something when I came back from mute? Hopefully it's picking up the audio. Okay, let's keep going here. This seems a little bit intense, like having to draw out an entire. If we remove this here, let me also view my stream myself. I know I'm sort of going off on a tangent here, but this is important to me, so I need to make sure that we're actually getting something good here. So if I watch my own stream, do I hear my voice? We're actually getting something good here. So if I watch, okay. Yeah, no, it sounds fine. I'm not sure why it's complaining. Okay, so what if we had our graph, right? Let's say it goes from 1 to 3, negative 1 to 3, and then 0 to 4. So let's say we had like 0 to 4. I'll just draw of like 1, 0, 1, 2, 3, 4. That's a really small line. Let's do something like this. And then we said we were going to do -1. Right, so this will be, yeah, let's just have this over here. And then we'll have some going this way. Like, the points they're presenting us are what? 1, 1, -1, 0. So we have one at 1, 1. Let's make this so, say this is 0, so 1, 1. I have one at 1, 1. We have one at 3, 4. 1, 2, 3, 1, 2, 3, 4. I have one up here. And then we also have one where? We have one at -1, 0. So -1, 0, right? So like, we can always move one optimal path. Does it say how we can? You can either move vertically by 1 unit, horizontally by 1 unit, or move diagonally, square root units. In other words, move 1 unit vertically. Okay. But these do not count as visits. We have to go through them in order. Sounds good. Awesome. Thank you. Yeah, it's weird because like YouTube was mentioning to me like over and over, hey, the bitrate, you know, it's lower than the recommended one, so make sure you're keeping up with it. So just to make sure, but that's good. Thanks for confirming, ECAS. So there's almost, I mean, like we have to go from, it just wants us to go in the order. So like we can't just do distance between here, from distance to here, and then from distance back to the first one. Like, can we just calculate all the distances? Distance, 2D distance calculator. Let me just try this out. So if we start at, I'm going all over the place here. If we start at 1, 1, so 1, 1 and 3, 4. 1, 1 and 3, 4 is equal to 3.6. Okay. Let's just write these out. I'm going to write these out right here. So 3.6 for that first one. Then how about we do 1, 1 to 3, or 1, 1 to 3, 4, and then 3, 4 to -1, 0. This is 5.6, so that's already, this is already looking bad because it's over the output. And then we do -1, or actually no, wait, what did I do there? 3, 4 to -1, 0. Oh, but then would I go from like 1, 1 to 3, 4? Okay. Oh, interesting. And then back to, okay, the shortest distance that crosses all these points. I mean, if I'm thinking about this sort of like a graph, I know like, well, if I move in this direction, or I can move in this direction, I can move in this direction. Like, I feel like I can move in an infinite amount of directions. When do I know to even start going back? I was just taking a second to drink some water. How do we even know to go back here? Minimum time visiting all points. All the points in the order given by points. What is the distance formula? The length of the path connecting them in a two-dimensional plane. So I mean, if we just had a straight line, like how does the distance formula work? What does that do exactly? Distance formula. Like I just want to know exactly how. Is it just the straightest line? No, okay, it's the hypotenuse. Is that what it is? Is it the hypotenuse? A to B? So if we just made like if I made like a triangle here, right, I guess it would be this thing. And then if I made a triangle here, it would be that thing. And then if we had a triangle here, it would be like this thing. So I mean, it wouldn't be this distance plus this distance plus this distance. Or can we go, or do we even need that? We can just go this distance here to this distance there. And we get to all the points, right? Why are they going back to... Oh, but it can be any sort of order. I mean, we can start at -1, 1, then go here. And we... Okay, we have to visit them in the same order. Can't just be that distance to that distance. Distance formula online. That's the one I just did. I just want to try a different one. Okay, here we go. Type 2D points, dimensions 2D. The first point is 1, 1. Second point is 3, 4. The distance is 3.6. Yep. Now, what if I round down though? Is that gonna? That's still not gonna give it to me, right? Because that's 3.6. Let's say I round down to 3. I mean, here I can do 3, 4 to -1, 0, and that's 5.6. That's 5. So that's 5 plus 3, which is 8, and the answer here is 7. Time from 1, 1 to 3, 4 is 3 seconds. Because we're going up, we're going this way and then that way. How else can we simulate this? All the points in the order given by points. If we start at 1, 1. I mean, if we go right, like what's the closest way to get there? If I go right, I'll just have 2, 1. I mean, that could be a solution. How would 3, 4 get me there? These do not count as visits. Minimum time visiting all points. This one's very tricky. For an easy question, I feel like this one's hard. This maybe at some point was a medium. Perhaps. But it shows up on the first page of LeetCode Easy, but remember, we're sorting by acceptance, and what I think happens is a lot of people learn this because they feel like it's very important. So a lot of people start solving it to just apply what they learned, and then the acceptance rate shoots up. Because it's like two-sum. Like two-sum has gone around like crazy, and it used to be, a harder question, but then once everyone started learning the trick, a lot of more people start solving it, so then it becomes like easier according to the acceptance rate. I think we're going to have to take our first hint on this one because I'm truly stumped. And if this is indeed a graph question, maybe we'll look at related topics. Okay, so this is array math and geometry, right? So the fact that we were using some math and geometry, right? Just based on this, I was trying to figure out distances with the hypotenuse here. Now, how do we get the shortest distance? Probably clarify what a distance is. Only way following sections if we stick, okay? All right. Euclidean space, distance formula for Euclidean distance. Other spaces. This is always a straight line. Okay. Strange things happen. Distance to a line and between two lines. Okay. Distance beyond length. Yeah, this is a lot of how to find the distance between 2 points. What is a click in a distance? Distance formula. Easily memorize it. SI, what is the distance from A to B? And that gives us that. Yeah, it's tough. Like, I really thought it would be something with distance. The distance formula here. Because the shortest line, I mean, that would be the fastest way to get there. That's the minimum amount of, like, distance we have to travel to be able to get to that point. So calculate the distance of these 2 points, right? 1, 1 to 3, 4. We can just go directly up here. That's like 3. But then to go all the way back down here, 1, 1, 2, 2, 3, 3, 3, 4. 2, 3, 1, 2, 0, 1, negative 1. 3, 2, and 2, 2. And what's 3, 2, and negative 2, 2? Does that even give us 3, 2, and negative 2, 2? That's 5. See, so that is the answer there. 3, 2, and negative 2, 2 is the answer. So why does it, maybe there's something, 1, 1, and 3, 4. 3.6. We round down to 3. 3, 4 to negative 1, 0. Negative 1, 0. 5.6. 3 and 5 is 8. It's not 7. This one is tricky, 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 tricky. Optimal path. Because I'm not even sure I have to care about the path. I feel like they explain to me the path, but I don't need to like really care about it. Because if I go, well, let me think about this. The shortest distance from here to here, plus the distance from here to there, right? Because that would give me all the points. I would go from there to there. But now wait a second, like, do I need to recalculate? No, yeah, I do, right? If I'm going from like, well, wait a second. Oh, but I also have to pass through all those points. Do I consider, like, if I've already been to 3, 4, I still have to calculate that too. I might have to table this one again and think about it a little more. This one is tough. Let's see one of the hints. To walk from point A to B, will there be an optimal strategy to walk? Advance in diagonal as possible, then after go in a straight line. So we just continue, and then here it's just repeat the process until visiting all the points. So we always go diagonal until we need to go straight. That seems wild. I mean, okay, that's cool. 1 to 2 to 3. If I go to the next one, that's 4, 4. So then I just go up to the next one. That's 1, 2, 3 to the next one. Then 3, 4, just go diagonal downwards until we finally get to the next one. 3, 2. How do we know to go down or left or right? Repeat this for all the different points. So I guess at any given time, let's think about this. I'll know that I need to go I can either go, right, I can go, well, we can go anyway. We can go left diagonal, right diagonal, down left diagonal, down right diagonal. Now that we know some of the hints, I think we're going to table this one for now, and we'll revisit it again, even maybe later on during this stream. But since we already know all the hints, I just sort of want to like take a break from it and let it mull. I need to mull in it for a little bit, let it marinate. That was the first one that we've taken a hint on. So pretty cool. Increasing order search tree. Let me see if I remember this one. I think, yeah. Given the root of a binary search tree, rearrange the tree in order so that the leftmost node in the tree is now the root of the tree, and every node has no left child and only one right child. Okay, I really want to draw this one out. I need to draw this out for my own sake. 5, 3, 6. So let me delete this. 5, 3, 6, 2, 4, 8, 2, 4, 8, 1, 7, 9. 1 all the way in the left and 7, 9. 1, 7, 9. Let's get all our arrows. Okay, and we have 5, 3, 6, 5, 3, 6, 2, 4, 8, 2, 4, 8, and then 1, 7, 9. So 1, 7, 9. Okay, let's see. So I want to take, like, I want to make this one the head, right? There's like maybe a couple of different ways I can do this though, and we'll find this out now. Like, what happens if I started, normally I always think about starting from the left, but maybe I can think about starting from the right. So let's imagine that I'm just traversing down here, making my way downtown. If I get to like the right, like, okay, I keep going right, I get to a null, I come up here, this is a leaf, I don't do anything. I come up here. Okay, so if I have a left, this is one thing I'm thinking, like if I have a left, I can go to the left and then return the left. Or I guess maybe here I'll do sort of the same thing again. I'll go all the way, but let's say this is a leaf node, so I return left. Then I'm at here. Maybe here what I can do is I can get the node that was just returned to me and set its right equal to this 8. So I could have something that looks like this perhaps. Apologies for the crude drawing here, but let's imagine that 7's right was 8, and then we sort of pop off this stack frame. I don't have a left, so I leave it. Then I come up to 5. Now I start going left. Okay, I go right. I guess I don't need to do anything. Oh no, I need to go right. If it's a leaf node, I can just not do anything, not worry about it. I come left. This is null, don't do anything. Come right, okay. Or the left one, I can return the left, set its right, something like this. I can return this, set its right, maybe to be something like that. This is already 4. And then here, set its right to be 5. I'm thinking something like this. I know this picture's like crazy, but let's see what we kind of just did here. I'm thinking, okay, so we go all the way to the right. We get here. This is a leaf node, so I don't think we need to do anything. But let's start writing out some of our ideas. It's a good way to proceed here. So if leaf node do nothing. All right, so we come all the way to the right. It's a leaf node. We go back up to here. Then we go to the left. Now, if we just... See, I can't do nothing here, right? Because we're at another leaf node here, and we definitely have to do something. Because there will be a case where I'm going to continue traversing on the left. But if I get to the leaf node, do I just return that? Maybe in the right case, like I say, go to the right, leaf node, return. When I return to here, I can just say node.right. Maybe I'll just sort of like naively set the right to the thing that was the right anyways. And then I'll go to the left. If the left is a leaf node, I'll return. and I'll say this dot right equals the current node. So maybe I can have something that if leaf node, I guess we'll just say return node. So let's do something where we have like traverse of right const right node equals traversed right. I'm just sort of, yeah, let's do that. Make this a little bit bigger, traverse right. And then maybe when we get there, here we can say if root equals to null, or if root.left equals null, or maybe just to make it a little bit easier, if not root.left and not root.right, we return root. So here I can say root.right equals to right node, which is like, we already know that, right? Then we can say const, I really want to I need to move all this stuff here. Oh, I missed my 1. That's fine. Let's move my 1 over there. Const left node equals traverse left. That's a leaf. So then maybe here we say the left node dot right equals root. I kind of want to go by this and see how far we can get. And I'll just say here return root, but let's kind of mess with this. So if root dot left, okay, no, so const right node equals traverse right. Okay, not a leaf node, so we traverse right. Not a leaf node, so we traverse right. This is a leaf node. This is a leaf node. So we return the root, and now we're here. Now this roots.right is just the right node that we got, so that's fine. Const left node equals traverse left. We come here. This is a leaf node, so we return root. Now we're back here, and we say the left node that we just returned, its right is now equal to root. So let me modify that one little section. Let me delete, or let me actually copy this 7. All right, I'm modifying this tree to sort of simulate what it would look like. Sort of in a situation like this, where now the 7 dot right is equal to this, right? And now we return root, which is fine. Or maybe I want to return, I should return left node dot right equals root. Maybe here I should return left node. So I return left node to this. So 6 just got done. 6 just got done doing its right node, right? And what I got from there was, so root.right equals right node, which was the left node. So this should now be set to here. Now it's going to try and get a left node. We go over here. If root, so this will be our second base case. If it's null, can we just return? Because now I'm going left. Okay. That's fine. Left node, traverse left. What do I want to return here? I don't really want to do anything. So what if I just say here? No, because we need to return something here. If left node, const left node. Maybe here we can say if root dot left, if not root dot left. If not root.left, then here we can have this piece here, const left node equals that left node. Okay, right? So in here, we're sort of protecting ourselves, and then we can still return the left node anyway. So let me see, I got done with my right, root.right equals right node. Okay, that's fine. But now I only return left node in this case. Return left node, else here I can just return the root. Right? I can just return the root, which should just be the 6. So I come back to 5. 5 just got done calling its right, so root.right is this. Now I say, okay, if not root.left, so if not null, or I'm sorry, if this should be if root dot left. Now we start going down the left part of this. So I go to the 3. Can I make this like not show up every time? Let me move this like up here. Let me again get all my, nope. Looks like I'm gonna have to, oh, here we go. Let's do this. I need to get my 9. To move this up here. Okay, so I just got done with this. Now we're gonna go, okay, if root dot left, const left node equals traverse left. Okay. Now we're at the top of our function. Const right node equals traverse right. Come up here. This is a leaf node. Now we say root dot right equals right node. So that's always the case. That's fine. If root dot left, we go left. This is not a leaf node. So const right node equals traverse right. Go over here. So maybe I should do the same thing. I should do the same thing here, right? If root dot right, if root dot left. Now, do we return? Maybe here we want to do the same thing, right? So if root dot right, open up another if in here. Can do this. Root dot right equals right node, and here we can say return right node. Right, so we'll get here. Let's kind of start from here again. So if root dot left, which it is, okay. Traverse left. Here we say if root dot right, we come over here, we return. If root dot right, we go right node. This is a leaf node, so we return right, root dot right. Okay, return right node. All right. Root dot right equals right node. Wait, I'm getting confused here a little bit now. Root dot left, if root dot right, const right node equals traverse right. Okay, we return the right node. So we're back here. Root dot right equals right node. Return right node. Now where I still need to, okay, return right node. So I'm back up here. Am I gonna go left? Am I ever gonna make it here? We might be onto something. What I like about this is there's some sort of pattern here, right? Like it looks decent, I guess is what I mean. Let me just run this and see what we can get. And this is increasing BST. So anywhere we have const right node is if root dot right. Anywhere we have traverse, okay. If root dot right, we'll call right node with root dot right. If root dot left and root dot right, return root. Root dot right equals right node, return right node. If root dot left, const left node, increasing BST root dot left. Left node dot right equals root, return left node, return root. So let's see what this does. 9. That's amazing. we didn't actually patch anything up here. If root dot left, if root dot right, const right node equals increasing BST root dot right. Let's start this over again. And we lost our image here, so we're gonna have to patch it up again. Let's create another one down here. Let's make this our 7. Let's connect them. Okay. Not a leaf node, so if root dot right node equals traverse right. Okay, we come here. Now we're at the top again. Root dot left, root dot right, we come right node. Perfect. Root dot left, nope, not a leaf node. Okay, come over here. Okay, so this is return root. All right, so now we have the root dot right equals the right node. Okay. Return right node. So this one, yeah, I need to go, maybe I don't need to, let's see, return right node, return left node. I just always have to root.right equals right node. Okay. If root.left, I can get that one. Left node dot right equals root. Maybe what I need to do is not return here. Inside of here, I can say left node dot right equals root, and root equals left node. And then inside of here, we can just return the root. Let's see how this works. Trying things out. I mean, I'm happy with like progress that we're making on this. But let's see. Error found cycle in the tree node. Okay. Let's go back to the drawing board here. So I don't want to return, okay, root equals left node, return root. Let's do root equals left node, return root. So we're at 5, and maybe this time I need to draw like I used to before, like each one of my different pieces here. So here I just called right node. Here I called right node. Here I called right node. Here I return root. So here my right node is the 9. And I remove this, right? Yeah. Root.right equals right node. Okay. If root.left, const left node equals traverse left. All right. We return root. Left node dot right equals root. Okay. To me, that sounds like we should be able to do that. All right. Becomes this. Come over here, draw this, remove this. Left node dot right equals root. And now the root, right? Because the root used to be 8, but the root should now be left node, which is this guy, and we return root. This just got done with this, so now the right is 7. Okay. If root.left, no. We can just return root, which is here. This just got done with its right. Oh. Return, no, yeah, that should be fine. Return root, because then root will just be this. There's no root.left. So we'll return the root from this stack frame, which would be this one, right? Because when this gets done calling its right, return right node, root.right equals right node. Okay. No root.left, so just go up here. This got done calling its right. Now it's 6. If root.left, const left node equals traverse left. Okay, this is not a leaf node, so now we ask ourselves, if root.right, we go right. This is a leaf node. So we return root, and now root.right equals right node. Okay, that's fine. That's always the way it was. If root.left, we go left. Okay, if root.right, which it's not, so we don't do anything. If root.left, we go left. Okay, leaf node. So now we're done calling the left here. Const left node equals const left node dot right equals root. So we should be back here. So if we cut this, do that, const left node dot right equals root. Root is equal to left node. Oh, this has to be, yeah, we don't want to return that. Const root. Yeah, now if I'm going left, it's a little bit tricky. Const left node traverse left. Left node dot right equals root. Now if root is equal to left node and I return this, that means when I initially went to my, when this comes back, I'm going to get the 1. But what I want is the 2. But then how do I keep track of this 1 up here? How do I remember that 1 that I just came from? How would I? And really on top of that, how I feel like this part we had this part. So maybe right is not the way to go about doing this. Maybe instead we need to go left. But we were extremely close here though, because would the left always allow for me to? I don't think so. It'd be nice if at the end, maybe I need to be patching these things up as I go along. Because here I'm also messing up the root. It'd be nice because right, this needs to become like, once I return this can't just stay like this. Needs to go way up here. It needs to become the parent of 5. And then we need to remember that root at the end. And how did we do it here? 8, 9, 7. I guess because none of these had children, but that's fine because this one still became, like, I returned this, then 2. I see root equals left node, return root. I had just gotten done with calling the left on 3, left node dot right equals root. So now we're gonna have, yeah, that's the thing. I think we'll end up with something like this, which this, this would, I guess, be our cycle, right? Multiple things pointing to the same one. Left node dot right equals root, and now root is equal to leaf node. We return this guy from the left here, so then we get something like this, and root equals 3, so that's not right. Close. I mean, I felt really good about this one. I thought we were gonna get there, and I know we can get there. Just need to keep thinking about it. What if we go the other way? I feel like going the other way would make things a little more complicated. So I think really where I need to focus is what happens. I'm gonna undo a lot. Like what happens in this case, right? As I start going down here. Somehow I need to slowly build this up, but like still retain my root. Increasing order search tree. If I start from the left, make this the parent of 2, make that the parent of 3, 4, make that the parent of 5, but then you got to return the root. 157 would be what? I mean, I guess we don't have to really do it, in order, right? Or no, rearrange the tree in order, so that the leftmost node in the tree is now the root of the tree, and every node has no left child and only one right child. Could we just process everything on the left first and then process everything on the right? Well, I mean, that's what we did. We processed everything on the right, and then we were going to start processing everything on the left. So in this case, we return this. This had nothing. If this had no children, if root.left, we would just return root, but that wouldn't give us what it is we're looking for. How is it that we got here? So const left node traverse left, root left node dot right. I don't want the left node dot right. I want this. Yeah. This one's also really tricky, even with the drawing here. I mean, I also don't know if it just wants us to, like, what if I just created a new tree? That doesn't sound fun though. I don't know if that's the expectation. Should I just be creating a new tree? I mean, we could try that and see what happens, right? So let's say something like search tree equals null. So we can say search tree equals null. And we can start now doing a, let's see, the first time I get to my null, I just return. And we can do is search tree equals, let me see, let's think about this. We have a left and a right. Let's just do like the standard in order algorithm here. So if root equals null, return root. Here we can do increasing BST root.left. And then we'll do increasing BST root.right. When it's null, so we got here it's null, and now we're over here, and this is like a valid place for us. So we can just say search tree, like search tree equals a new node, and then search tree.right. I mean, I guess I could say that. Maybe I can just create a new list node here, or a new tree node. And then here every single time search tree.right equals new tree node with root.val. And then search tree.right equals new tree node of root.val. But then we also need to like return. I can't also do like search tree equals search tree.right. And then every single time we'll do something there. And how do I maintain, right? Because if I just do return search tree here, that's just going to give me 5, right? That's just going to be like the end. Can we keep track of, let's see. I can just keep appending to that and just always keep like a link to the root. Sort of like a sentinel value, if you will. What if we had, let's see, if not root, return root, let sentinel equals new tree node. We can do this. New tree node, and then as we go along through here, perhaps here I can do const in order equals root. I can do all this stuff in here. Equals null, and then instead of in order we'll do this. Here I can say sentinel.right equals new tree node root.val, sentinel equals sentinel.right. Return search tree, we can just do all this all the way till the stack is done. Here I can say in order root, return sentinel.right. In order root, this will go all the way. Let's see what this gives us. Does it return a tree node? Okay, so sentinel is a new tree node. In order root.left, we go all the way down, we come over here, sentinel.right is equal to a new tree node with root.val, and then sentinel equals sentinel.right. Okay, in order right, that's nothing. Come over here, sentinel, oh, does it want me to also have nulls? Well, sentinel, I am so confused about this one. I'm done processing the left. I go to the left. I come here. Sentinel.right equals new tree node root.val. Okay. Am I not calling this correctly? In order search tree. Let me remove this. If not root, return root. So if it's not, if it's null, right? So opposite of null equals true. We can just return the root. Sentinel, because what do we get here? We just got an output of that. Sentinel equals new tree node. In order root. If root equals null, return root. Maybe just to be a little more, I mean, I could just get out of this one. Still empty. In order root dot left, sentinel dot right, new tree node, root dot val, right? Sentinel equals sentinel dot right, in order root dot right. It's not clear to me why that wouldn't work. Root dot left, root dot right, return sentinel dot right. You want me to return a tree node? Should we console log in here and see console log sentinel dot right? Maybe let's put this one here. So 1, 1, 2, 3. Okay. This is fine. We should be modifying this going along. Sentinel dot right equals. Oh, wait a second. I'm changing this pointer every single time. Let sentinel equals tree node. So then inside of here, maybe what I can do is I can just create. Yeah, I can start creating it at the moment. Yeah. Sentinel dot right, and let's say sentinel head equals sentinel. Sentinel head dot right equals new tree node. Sentinel head equals sentinel head dot right, and then return sentinel dot right. Let's see what this does. Okay. Now I'm not like, if this works, which it might based on these test cases. Let's see what we get in terms of time complexity. 64.19. So presumably, what are weekly roundups about, right? The reason that we have this weekly roundup is because it takes, like, the fact that I wasn't able to solve these questions before, it means that these questions are more tough. So you can expect for these, like we've solved, this will be the second question. You can expect for these streams to be longer and for us to have to go through more questions. Or less questions, actually. Let me see. Let's see the solution. In order traversal. Construct new nodes. So it wants us to create new. Okay. Construct order on the fly. Okay, so Oracle should be on straightforward, repeatable. Curve right equals curve equals no, vary by style. Super hard problem. I think there should be a medium problem. Okay, so let's think about this. Like O of n and then space complexity is O of n. Okay, so it looks like the recommended solution was to go about the way that we did it, or a solution. So that's good. And time complexity says, you know, we're doing all right. But discussions are probably going to be like, oh man, it's, you know, super easy. Don't need the condition of BST, just in order output the whole tree. Let's see. Okay, yeah, this is going to be, well, I want to figure out that solution on my own. I don't want to look too deeply into that one. 97.8, it means we're doing good. But again, I will personally do this again, sort of like in place without using an auxiliary data structure like I did with this Sentinel, because I feel like I was close. It's just a matter of me knowing how to manipulate my pointers. So this was a pretty tough question. I feel like it could very well be a medium question for the follow-up. I think even something like this, you'll get some mileage. Like it's pretty difficult, but I'm glad we were able to get to it. And let's just go to another one. Increasing, decreasing string, whatever that means. Okay. Following algorithm. Pick the smallest character from S and append it to the result. Pick the smallest character from S, which is greater than the last appended character to the result, and append it. Okay, I think I know what we can do here. We can just A, B, 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 C, C. We can do A, oh, and then we need to do B. Then we need to do C, B. No, A, B. All right, it wants us to do, oh, pick the smallest character from S and append it to the result. Greater, okay. So we pick A and B. Then we pick, wait, what? Oh, pick the smallest character from S and append it to the result. Smallest character from S, which is greater than the last appended. So we have A, B, C. I can't do any more. So now we go backwards, C, B, A. A, B, C, C, B, A. Ah, okay. I think what I can do here, so pick A, R, T, and then go backwards, picking each one. Yeah, okay, this one, I see what we can do. We can keep a frequency. I guess the order frequency, this is what, lowercase English letters. What if we created an array here where I can say const alphabet equals to new array of 26. I'll fill this up with 0. We'll go through each character of S, and we'll say alphabet of C equals alphabet of C plus 1 or 1. So we're sort of loading up on frequencies. And now what we can do, let's think about this. Let's say const length, right? We can say let string length equals to s dot length. We can say while string length is greater than 0, we're gonna sort of go back and forth in alphabet. So what I can do is I can create 2 for loops in here for let I equals 0, I less than alphabet dot length, I plus plus. Before I write anything in here, I'll just do the next one for let I equals alphabet dot length minus 1, I greater than or equal to 0, I minus minus. Here I can say if alphabet of I is greater than 0, then I want to pick the character at this index. So I can say const char is equal to string from char code of I plus 97. I can append that to my result. All right, we can say result dot push char, and I can decrease string length minus equal 1. I'll go over what this I plus 97 thing is. All right, and then similarly here, if alphabet I is greater than 0, we'll create the character code. We'll push the character, and then string length minus equals to 1. Here we're just going back and forth, right? We're picking, yeah, we pick one, we do it, we go to the next one, do it, go to the next one. Okay, now we start from the back, pick the next one, and then at the end, this will be 0. We have no more characters. Return result dot join. Let's see what this yields. Okay, obviously we're missing something here. While string length is greater than 0, if alphabet of I, so we have alphabet const c of s. Oh, wait a second. We need to put this like const index equals c dot char code at c minus 97 to normalize it. Alphabet of c equals, okay, let's do this. Still, oh, of course, I need to do it at that index. Time limit exceeded. Let's see, ABC, CBA, ABC, CBA. Let's get other test cases. Oh, why did we double count rat? I should only have, let's see, +1 or 1. So I should do the R once, the A once, the T once. So I go with alphabet I greater than or equal to 0. And of course, we did not result.push car. We need to do alphabet of I minus equal to 1. Similarly here, alphabet I minus equal to 1. I went through this one very quick. Obviously, that kind of bit me in the butt a little bit. Let me submit this, see what we get. 26.56, so we passed. Perhaps not the fastest way of doing it. Okay, 100%, that's wild. But let's sort of like think about this here. Let's think about the time complexity, right? We're creating a new array, but it's going to be, it might take constant time. I don't know. I'm not sure if this is just like a constant operation. Like, what is the time complexity of creating a new array with certain length? Maybe that's just O of 26. I'm going everywhere here. Wow. Karate. I hope that's a decent wow. I hope it's a wow of like, oh, that's cool. Not a wow of like, oh man, this is not good looking code. But anyway, let's think about this here. Appreciate the comment though anyway. So let's imagine this is O of n or O of 1. I'm not really sure. Or let's look it up though. Time complexity of creating an array. O of n. Okay, so it's O of n of creating a new array. So this is O of s. No, this is O of 26, right? So really it's just O of 1. It's always going to be constant. Time complexity here for const C of s, this is O of s. Okay, while string length is greater than 0, so this will be also O of s. You'll have to at least go 7 times. Over here, this is O of 26, right? And then O of 26, right? So O of 26 plus O of 26 is just O of 52, so it's just constant. So really it's just O of s. So this whole thing ends up being just O of s, linear time complexity, right? The space complexity is also going to be constant because the only thing that we're creating is this. Well, I guess we can consider the output array. The output array will be equal to, let's see, however many, it will just be equal to the same thing, right? So maybe this is constant plus size of s, so just the size of s for space complexity. But this piece right here, can we do better? Maybe instead of, I picked the first one and then I picked the last one, but I need to get there to be able to know. I wonder if I can do, no, I need to pick all these in order, right? That's one thing that I really wish. It'd be nice if I can do like, oh, do maps keep, yeah, wait a second. MDN map, does this insert in the order? Remembers the original insertion order. This might be a little more elegant, but I'm not sure if at least when we're like, as far as the compiler goes, we might be able to get some optimizations by using this like static sized array, right? One thing that I could think of doing that would really like boost this up is these are both the same thing. So I could say, let's see, for example, like function handle car addition. Let's just do, well, let's just make this normally how I do it. Console handle car addition where character, that's car stands for character, right? If I move all this here, what do we need? Car string.code, so we need I plus 97 result.push car, alphabet of I, string length, okay? So here we could say handle car addition I, and maybe just do all this. Make this like a little cleaner. All right, so we can remove this, we can remove that. While string length, okay, and then we have our result. We should get the same thing here. If I run this, art and art, 76.56. So let's see what discussions have to say. 2 clean codes with explanation and analysis, C++ counts. Let's see. Specify descending order, no matter what order you put it in. Can you explain why this works? Use tree map to count each character in S. Sort order, decrease the count of each key and remove the entry if reaching 0. Do the similar operation, but in descending order of the keys. Right, so while it's not empty, descending key set, where's the one that we get the increasing? For car C, same as, okay, use array instead of tree map to get better time performance, right? Return answer to string. Append the key, decrease the count. If the count reaches 0, remove the key from the counter, change the direction. Same as, okay, delete. So it just seems like we're going back and forth here. Let's see what this person did. Okay, yeah, really, really exactly what we did, right? You just go C++ counts. Okay, so this is a weird one. Like I didn't think, like I haven't done a solution like this before, but this is what I mean by don't like marry a solution, because you just really don't know. You just don't know what you might come up with at the time that you're solving it. All right, let's get to the next thing. Sum of digits in base K. Is there an easy way? Okay, this one I felt like it was a mathy thing. The sum of the digits, 5 plus 4. Yeah, is there like a, let's see, sum of the converting n from base 10 to base K. Convert number from base JavaScript. Is there like a method for this already? That'd be nice if there was like, oh my god, are you serious? Parse int? Wait, does that actually work? Does parse int do that? Wait a second, that would be overkill. That'd be amazing. Parse int of 34 in base K. Oh. Expressed in base 6. Oh, wait a second though. We want expressed in base 6. No. To convert to a number from a hex string. To convert from a number. Okay. How do you convert numbers between different bases? To convert a number from a hex string, optional. A number from 2 to 36 that represents the numeric. Okay. Number object to string. So how would that look like if we did, wait, is number yeah, okay. Number to string. Oh, okay, wait, let's do let my num equals new number of 34, my num dot to string base 6. Oh man, really? Wait a second. Okay. See, because like this, I feel like this is just a math problem. Like if you don't know how to convert, from one base to another, like I didn't know how to do that. I haven't done that since university, and that's been 5 years ago. So let's see. Const my number equals new number of n. Const to base equals my number dot to string of k. Here it can say parsed num equals parse int of to base in 10. And then here we can just do the trick where we say let sum equals 0. Here I'll make this a let while parsed num. I can say const digit equals parsed num modulo 10. Sum plus or equals to digit. Parse num equals math.floor of parse num divided by 10. Return sum. Will this work? 9 and 9. Took a little bit long. The fact that it took that long makes me think there's got to be like there's probably a super fast way of doing this. 9 and 1, 9 and 1. Maybe all this different conversion is crazy. 13.46. Okay, I am gonna look up the solution of this one because that probably some like library that just does this. Mod and divide with analysis. C++ simple, just adding remainder. And log n. Sign complexity log n because with every iteration we're decreasing the problem space by n divided by k. Well, n over graded sum plus or equals n modulo k. Wait, what? Sum is 0, while n is greater than... Wait a second. Really? So, is it because here we always do modulo 10, but what if we do modulo... No. You're kidding me. So while n, const digit is parse num modulo k, digit parse num, or n equals math.floor of n divided by 10. Well, that 7 and 1, is this, so also by k here. So is k the thing that decides how, well, I guess it should be k, right? Because we, wow. Immediately faster. Significant increase in time complexity here. Or, I mean, performance. Okay, yeah, this is, I guess, an interesting question. It's, I mean, if you remember how to do the conversion, maybe this is the formula to do a conversion from one base to another, and frankly, I just forgot. But hopefully now it'll stick in my head. Now I kind of know that, like before, maybe for normal questions, I always do 10 because we're in base 10, right? But this can really just be any digit. In this case, it's going to be the base. Okay, nice. I like it. A number after a double reversal. We're almost at 2 hours here, which is insane. I think I might wrap it up here, since we've been going for a while, and I do have some other things I wanted to take care of today. Yeah, so weekly roundups, like I said, generally, we're going to be focused on questions we didn't solve throughout the week, which means, let's see, like we started at 101, and today we are at 105. Okay, so we solved 4 questions, right? It's going to take longer to solve questions during weekly roundups because they were hard to solve during the normal LeetCode live sessions. So you won't expect to see, 7 or 8 questions like we normally do on a weekday because these are harder. But that's fine, and I think that's like truly what the intent of the weekly roundup stream is. So to everyone that watched today, really appreciate you all sticking around and watching it. I hope you all learned something. I certainly did. These questions are getting harder, which is awesome. That's really what I want. We cannot get better unless we challenge ourselves, right? So I really hope to see you all tomorrow. I'm going to be resuming the normal LeetCode live sort of style video tomorrow. Something I changed here on my main channel, you can see that I have a playlist for LeetCode live, and I also have a playlist of weekly roundups, so you can see all of them. And funny enough, it looks like the first one, I didn't even remember this, the first one also was around an hour and 40 seconds. So with that being said, I hope you guys all enjoy the rest of your Saturday. I'm looking forward to continuing to work with you all and getting better at LeetCode and achieving our goals. And have a great rest of your day, and happy coding. Later.